Good morning, welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been first in this course we looked at various kinds of power electronic converters such as DC to DC converters and DC to AC converters, etc. Now, we are looking at this question of pulse width modulation. We are just beginning to look at this issue of pulse width modulation. In fact, in today's lecture we are just going to see what is the purpose of pulse width modulation. So, that is what we are going to see in this in the coming couple of lectures. So, why do we need pulse width modulation? That is the basic question that we are going to address here. Now, if you look at this, what you need is you have a voltage source inverter and that voltage source inverter has a DC bus voltage. It has a DC bus voltage and the DC bus voltage is by and large fixed, it is not varied, I mean it is fixed and it could possibly be unregulated. You mean you can have a DC source, this inverter may be fed from a DC source and that could be a DC source such as an active PWM rectifier or in some kind of controlled rectifier, in which case that could be well regulated. On the other hand, it could be simply a diode bridge rectifier with some L filter, I mean with a C filter or an LC filter, in which case the DC bus voltage could also be unregulated. So, what we have is let us ignore this regulation or unregulation for the time being. Now, let us just say it is fixed at a particular value. So, we want to realize whatever fundamental voltage we need on the AC side, we need certain fundamental voltage, let us call it V1. So, given certain DC bus voltage which we can call it as VDC, we want to realize this V1 and who should do this? It is the PWM converter should do this now. And the inverter as such can produce a range of fundamental voltage for this given VDC. Now, you want a specific voltage, let us call it 60% or 70% or whatever. So, now the first goal of this pulse width modulation is to ensure that the fundamental voltage has the desired amplitude, that it should have the desired amplitude is one of the first goals, that you need to control the AC side fundamental voltage now. So, there are other cases you may also have to control the frequency of the fundamental voltage and there is also about the phase of the fundamental voltage, etc. So, controlling the AC side fundamental voltage given a fixed DC bus is one of the goals of this pulse width modulation. Beyond that, what happens is what you produce on the AC side is not a sinusoidal waveform. We are trying to synthesize some sinusoid of some 50 hertz or whatever modulating frequency, but it is essentially a non-sinusoidal waveform. We are trying to produce AC using DC. So, it is what you are applying basically is not a sinusoidal waveform. We apply various pulses, we may apply positive pulses during the positive half cycle and negative pulses during the negative half cycle and so on, and it is not a sinusoidal waveform. It has some non-sinusoidal, it has certain harmonics, it is non-sinusoidal. So, when you say non-sinusoidal, it has certain harmonic voltages. So, these harmonic voltages are going to result in certain undesirable going to have certain undesirable effects. This harmonic voltages will cause certain harmonic currents to flow, and these harmonic currents, for example, can go about increase the losses. These harmonic currents will now flow on top of the fundamental current through all the line side components. So, it could be a line side inductor or it could be an induction motor, whatever it could be. So, these are going to increase the losses and sometimes the core losses in those reactive elements and the motor can also increase now. So, what happens as an effect of the harmonics is that the losses are increased now, and then you in case of motor drive you may also have a pulsating torque. What you normally have in a motor, in an induction motor fed from a sinusoidal voltage sources, the torque is steady, you get a steady torque because it is the result of interaction of two different fluxes or one flux and a current or whatever, and both are sinusoidal. And if you look at them through phasors, we will deal with all this at a later date in a greater detail, but just to help you grab this, you have two fields, one pertaining to the stator and another pertaining to the rotor, which both revolve at the same frequency and they have a fixed phase angle. Because of the interaction between the two, you produce a steady torque. But what could happen in a motor drive is that you have not only sinusoidal voltage, but you also have harmonic voltages getting applied there. Because of these harmonic voltages, you can have harmonic fluxes and harmonic currents. The result of interaction between a fundamental current and harmonic flux or between steady flux and harmonic currents, you get pulsating torque, as we will see later now. So, these are some examples of the harmful effects of harmonic voltages. So, pulse width modulation, what it tries to do is, it first tries to give the desired fundamental voltage V 1. Now, this voltage V 1 is achievable through a number of means. So, now you can use this, and you select a particular method of producing this V 1, which results in certain amount of reduction in the harmful effects of the harmonic voltages now. So, the pulse width modulation has its second goal, this mitigation of the harmful effects of the harmonics. Sometimes you may say, I do not want specific harmonics. You can say, I do not want fifth harmonic, I do not want seventh harmonic, etc. That is what is known as harmonic elimination. Sometimes you might want to reduce certain harmonic currents in certain range, etc. Sometimes you might want to reduce the pulsating torque. So, your goal could be different, but overall, what can be said is, it aims at, the pulse width modulation aims at reducing the harmonics and their harmful side effects now. So, this is what I would call as the basic purpose of pulse width modulation now, and we go further to see how we control fundamental voltage and how to calculate harmonics and how to calculate the harmonic currents and things like that now. So, moment I said that it is a PWM waveform, these are some examples of waveforms that we will see in DC to AC converters. So, the first is basically a square wave now. You can regard this as your pole voltage V or O. That is, if you look at the pole, I mean the midpoint or the load terminal of a leg, and measure it with respect to the DC bus neutral at the midpoint of the DC bus, this is the kind of waveform, and if the inverter is switched in a square wave fashion, this is the kind of voltage waveform you will get. This is your pole voltage waveform now. So, this is a periodic waveform. So, similarly, you can modulate in several ways, some examples which we have already seen now. You can modulate in all these ways, all these are periodic signals now. So, many of such simple PWM waveforms are periodic signals. So, what we can do is, we can use Fourier series. We want to calculate how much harmonic it has, I mean how much fundamental component it has, how much, whether it has a specific harmonic or not, and what is the amplitude of that harmonic and so on. So, what we can use Fourier series to do that now. So, what is Fourier series? You may have any periodic signal, you may have a periodic signal, and this periodic signal may have any shape, does not matter, but it can be expressed as a sum of several sinusoids. It can be expressed as a sum of several sinusoids. So, let us define these sinusoids a little more closely. So, these sinusoids may have certain frequencies. Firstly, it could be 0 frequency, or there can be DC now. Next is, it can have what is called as the fundamental frequency, that is the same periodicity as the actual waveform, and it can also have harmonic frequencies, which are integral multiples of the fundamental frequencies now. So, periodic signal can be decomposed into a DC component, a fundamental component, and a set of harmonic components as indicated here now. So, here what I have given is some f of omega t. It has been the variable, instead of time I have taken angle at the fundamental frequency. Here omega is equal to 2 pi upon t, where t is the time period of the waveform in question. So, we have expressed this as a function of the angle at the fundamental frequency, or what we will call as the fundamental angle. So, now this f is f of omega t could have a DC component, which is given by this a naught by 2, and it could have several other frequency components. One of the frequency component could be omega itself. So, if you look at the frequencies, 0 is 1, that is DC, omega is another one, 2 omega is 3 omega, 4 omega, and so on. This can have all these various frequencies now. So, Fourier series helps us expand any given f of omega t into such a series. So, it helps us calculate the coefficients of various terms. I mean, once we are able to calculate the coefficients of various terms, we know how much harmonic is there. For example, in this term, if we can calculate a naught, we know what is the DC value, which is a naught by 2. If we can calculate a 1 and b 1, we know what is the sinusoidal component. It will be a 1 squared plus b 1 squared, and the root would be the amplitude of the fundamental component here. If you want the nth harmonic component, we must try and get this a n and b n here. So, let us move on to see a few more periodic signals now. So, this periodic signal, these are all periodic because they repeat over this with this periodicity t. So, now they are defined over f of t plus capital T is equal to f of t, and t is this period now. One example that has been given is a waveform ramps up and then falls back, and then it is 0, and once again the same thing begins, and this is your time period now. This is one example of a periodic signal now. Another example is given here: current rises, stays flat, falls back, and then it is 0 for certain amount of time, and this is your time period t, and the same thing repeats now. So, these are also certain other examples of periodic signals. Now, in this case, there is a difference between the previous one and here. The previous ones were all by and large AC waveforms. These were all by and large AC waveforms, and they did not contain any DC component at all. They have a 0 average value. If you look at this, it has a 0 average. That is, if you look at the area under this and the area enclosed by this, they are equal, and they have just have an opposite sign. So, if you look at the total area within over a cycle, it is 0, it has no average value, but these are certain examples of signals which have some average value. So, if you look at the average here, this average, when you average it over this 50%, the average is somewhere like this. If you average it over the entire cycle, then it is something like this. So, in this case, actually 2.5 is the average value of this current that you have now. So, if you look at the other case, the average value here, if you look at over this, it is also possible for you to calculate certain average like this. It is possible for you to calculate certain average like this. So, these are examples of some periodic signals which have non-zero DC values, they have some average values, and these are actually taken from some DC-DC converters. These are some current waveforms in certain DC-DC converters. They always have certain DC component flowing, whereas in DC to AC converters, when you are looking at the AC side, there is no DC component, they are all AC waveforms. These waveforms would typically have fundamental and other harmonic frequencies, but not the DC. So, that is what I said here. So, these are examples where they have no average value. You integrate this whole waveform, you can consider the first waveform, integrate it over the with respect to d omega t, start from 0 to 2 pi, and you find that the value is 0. You integrate this waveform, you will also find that it is 0. You can take the third example also, you do that integration, you will find that it is 0. That is because these are waveforms on the AC side of DC to AC converter. Now, these are all essentially AC waveforms. Ideally we wish that they were sinusoidal waveforms. So, like what we want to see here is some sinusoidal waveform like this, but then it has several other non-sinusoidal components which we cannot help because we are producing AC using DC. We are applying basically positive DC pulses and negative DC pulses to get something like this. So, what we are trying to do is, now the width of these pulses you can see controls the fundamental voltage, which is one of the purposes that we were talking about earlier. And now, if you look at here, this could also have some AC waveform, but in such there is some fundamental component. In such cases, this is one example where the harmonics could be a little lower than, let us say, if all the pulses were of equal widths. You need to do a complete Fourier analysis to expand them as Fourier series to get the exact magnitudes of how much etc. here. So, once again going back to the Fourier series, these are examples that we will have no average value now. So, the average is taken off, there is no DC component now. So, then let us look at the fundamental component now. So, we want to understand what is the amplitude of the fundamental voltage. So, if you look at this waveform, the waveform certainly has a fundamental component like this. So, the fundamental component is a sinusoid of the same periodicity as the original parent waveform, right, and we are also able to judge the phase. This should be the phase of this sinusoidal waveform. What we do not know is this amplitude. Let me call this as V1. We do not know what is that amplitude. So, how can you calculate that? So, what we need to do is, going by Fourier series, this waveform has several frequencies, like 0, omega, 2 omega, etc. Now, we know that for sure that it has no 0. So, it could have all these frequencies omega, 2 omega, 3 omega, etc. It could have all these frequencies. So, we still do not know. Now, we are interested in finding out the amplitude of the fundamental frequency. So, how do we do that? So, what we need to do is, if you multiply this waveform by a sine, let us say we multiply this waveform by a sine waveform. Let me just choose a different color here, maybe this. Let me multiply this by a sinusoid of the same frequency as the fundamental component. Why do I do that? And if I do that, why do I choose the same frequency as the fundamental component? Now, this waveform in question has several components. Let me write them as V 1 sin omega t, for example, plus some other, let me say certain V n, or some V, okay, let us say V 3 sin 3 omega t plus so on. It has all these various components. Now, if I multiply this by sin omega t, what happens? You first have this product. Let me once again change the color to something a little brighter. So, now let us say this sin omega t and sin omega t you have. This product gives you sin squared omega t, it gives you a sin squared omega t term. So, what you will have is basically this will become V 1 sin squared omega t, and the second term will become V 3 sin 3 omega t sin omega t, and so on. So, you will get some waveforms. If you look at this, waveform, and if you find out its DC value, its average of this term over a cycle, it will have some DC value. So, this average value is a measure of what is your V 1. If you consider this waveform, for example, sin 3 omega t into sin omega t, you look at the product waveform and you integrate it over a cycle, its average value will be 0. So, all the other components also, their averages, all the product terms that you will have here, their averages over a cycle will be 0, except for this term. So, how to get this, what you need to do is, you given waveform, you multiply it by sine of the same frequency, and the sine can be unit amplitude. Now, what is the phase of the sine? In this case, the sine is defined as sin omega t. Now, what we are trying to do in this case is, we are trying to do V of omega t multiplied by sin omega t d omega t, and we are integrating this from 0 to 2 pi, and this is 2 upon 2 pi. This is what we do to get our amplitude of the fundamental component. This is what you need to do to get this now. We are multiplying it by sin omega t, and because this is what is called as, one way to put this is an example of what is called as an odd function. So, if you extend the waveform to the left side, whatever is its value at some theta, at this minus theta it will have the negative of it. So, in these kind of cases, the waveform has only the sine components and does not have the cosine components. So, for example, if you go through the previous ones, so it will have only this b n coefficients listed here, and it will not have this a n coefficients listed here now. So, this is one. So, you know that you have to multiply this by a sine function here now. So, let us look at it more. Let us say the waveform is considered differently, or the same voltage waveform, let us take it like that. This is the omega t, the same plus V and the same minus V. Now, what we have is, this is 90 degrees, this is 270, and 180 comes in between. Now, this is the nature of the waveform now. So, in this waveform I am trying to see what is the fundamental component. So, what should I do now? The same way, but what I have to see is its fundamental. I can see that its fundamental is something like that. Its fundamental has its face like this, its fundamental is something like that. So, I need to multiply this by a unit sign. As shown here. So, what I do here is, I have V of omega t as defined here, I multiply this by cos omega t, and I integrate this with respect to omega t from 0 to 2 pi and 2 upon 2 pi. I do this to get the fundamental amplitude. So, here this is a case of what is called as an even function. This is a case example of what is called as an even function. if you look at the negative values, you go along the negative axis, you extend this to the negative horizontal axis also, you will see that this waveform is symmetric about the vertical axis. So, V f minus omega t will be basically equal to V f omega t. So, that is the kind of symmetry, and that is what is called as an even function. In such cases, the B terms do not exist, but the A terms, A coefficients in the Fourier series will exist. So, you go about doing it now. So, let us take it more generally. Now, let us say my waveform is something like that. This starts at some angle phi and it goes on till some angle 180 plus phi or pi plus phi, and this is 360 plus phi. In such cases, if we do not know what this phi is, or if we are unable to see, I mean, or in any kind of a general waveform, what we need to be doing is, we need to multiply this waveform by a sine component, by sine omega t, and do the integration over the cycle. And also similarly, we must multiply the waveform by cos omega t also and get this. So, this multiplication by sine and averaging over a cycle gives one component of that, and by doing it, the other component is available, what are called as A1 and B1, both these components have to be evaluated, and then from A1 square plus B1 square under root will give you this amplitude. That is your actual way of doing it now. So, what I can see is we can kind of generalize now. In the earlier case, you multiply it by a unit sign as shown here. In the second case, you are multiplying it by a unit sign as shown here. Now, here what you should be doing? You must actually be multiplying it by a unit sign. You must actually be multiplying it by a unit sign like this. If you can multiply it by a unit sign such as shown here, you do your integration over a cycle or take the average of the product, then we will get the amplitude. I mean, the average value is proportional to the amplitude of the fundamental voltage. So, what is being done if the phase is known? That is what we are trying to do is, we are trying to multiply by a sine wave. What is the frequency of the sine wave? It is the fundamental frequency, that is the same periodicity as the parent waveform in question, right. Now, what should be the amplitude of the sine? It is unit amplitude. Now, what should be the phase? The sine actually should have the same phase as the fundamental component of the original waveform. In this case, we are able to judge that. In certain cases, we may not be able to judge that. If we are able to judge that, or if we know that, then we can multiply it by a sine which is in phase with the fundamental component of the original waveform, and we can do that integration of the product and get the amplitude out of that. When we are not aware of the exact phase, what we should be doing is, we must multiply this by sin omega t and also by cos omega t, get both those A1 and B1 terms, and from there get the overall amplitude from doing it here now. So, this is how you determine the fundamental amplitude of the fundamental component. Now, let us say, how do you determine the amplitude of second harmonic? So, here we multiplied, as we saw a little earlier, we multiplied this whole thing, what is within the bracket represents the waveform. We multiplied by sin omega t because we were interested to see whether there is any omega t, sin omega t term exists. We wanted to find out the amplitude of the fundamental frequency now. Now, if we see that there is a second harmonic could be present here, what we must be doing is, we should be multiplying this by a second harmonic. We should multiply this by a second harmonic sine wave. So, let me say that I am multiplying it by a second harmonic sine wave like this. Right. Well, this is a second harmonic sine wave now. I want to get the product of these two. What would be the product of these two like? Now, let me consider some point. Let me consider certain instant here. Let me call this instant as theta, and let me consider another instant which is 180 degrees away. So, what do I find at these two instants? I find that the even harmonic has the same value at these two instants. I consider theta and I consider pi plus theta or 180 plus theta. At both these instances, the second harmonic has the same value, because this pi is measured at the fundamental angle. 180 degrees for the fundamental is one complete cycle for I mean what is 1/2 cycle for the fundamental is 1 full cycle for the second harmonic. So, it has the same value. Now, how about the waveform in question, that is the square wave here that we have considered. Let me take this. So, the square wave has this value, and what is the value here? So, here it is plus V, here it is minus V. So, the value at 180 plus theta is negative of whatever it is at theta. If you take this product is something at theta, and what is the product at 180 plus theta? It also has the same value, but it has a negative sign. When you add these two add up to 0. So, in such a way, this it is not only at this instant, you take any other instant. So, you take here and you take the corresponding instant there. You will always find this is some other theta dash and 180 plus theta dash, any when we are looking at some arbitrary angles. So, you will find that at both these instants the even harmonic, I mean the second harmonic or any even harmonic for that matter would have the same value, but now the waveform in question is such that its value is the negative of the other. At 180 plus theta is the negative of whatever it is at theta. So, such a waveform has no even harmonic. You consider the same thing here also, you consider this angle and this is at 180 plus theta. So, this waveform also has no even harmonic. You consider this waveform, you consider this angle and you consider this at about 180 degrees later. The waveform here, whatever value it has at V of theta, at 180 plus theta it has a different value. So, whatever the waveform is at 180 plus theta, it is negative of its value at theta. This is what we observe in all these now, and whenever this condition is satisfied, there are no even harmonics. This is what we call as half wave symmetry. I should caution you that the symmetries are defined in slightly different terms by various authors and all that. So, we are trying to define it for the purpose of our course. Here when we say half wave symmetry, what we mean is that the waveform in question satisfies this property. If you consider the waveform at theta and at 180 plus theta, where this angle is a fundamental angle at the fundamental frequency, then whatever is its value at 180 plus theta will be the negative of its value at theta. That is, so an example of this is the square wave, and all the other PWM waveforms, there are a couple of other PWM waveforms we saw earlier also satisfy this particular property. So, this half wave symmetry basically means no even harmonics. So, if you multiply this 180 plus theta here at sin 2 omega t and sin 2 omega t, which is what we just saw right now, if you do that integration over a half a cycle or a complete cycle, you will see that the product, I mean you multiply this waveform by sin 2 omega t or sin 4 omega t or sin 6 omega t or anything like that, you will always integrate it over a cycle, you will find that the product has 0 average. So, it has no even harmonics. So, the significance of half wave symmetry, whenever a waveform satisfies this condition 180 plus theta is equal to minus V of theta, you have no even harmonics present there. Now, let us look at certain examples of half wave symmetry. I mean examples of waveforms that exhibit half wave symmetry. Sine wave of course has half wave symmetry, because sine of 180 plus theta, let us say if you want to take sine of 90 degrees is basically minus sine 10 degrees. So, it has that. So, all the sinusoidal kind of waveforms with whatever phase shifts you consider, they all have this cosine or whatever you might call now. Certain other examples that you can think of, or I am just giving some arbitrary examples, let us say a trapezoidal wave, let us say a trapezoidal wave. This waveform also has half wave symmetry, I mean the slopes are equal here, there are certain drawing inaccuracies, but the slopes are actually equal, it is some plus V and it is some minus V here. So, if you see here, whatever is the value at theta, the waveform has the same thing at 180 theta. This is 360 degrees or what corresponds to t in terms of time, and this is 180 degrees or what corresponds to t by 2. So, this is 180 degrees, this is 180 degrees. So, whatever it is at theta, if you take 180 plus theta, the waveform has this property that at 180 plus theta its value is the negative of whatever it was at theta. So, this is one example of half wave symmetry. Like this you can go about forming several such examples that you can go on giving. Now, let me say, shall I draw, let us consider a triangular wave. This is a complete triangular wave, this is the time t now, this is time t by 2. Here also if I see here and I consider another instant which is 180 degrees away, whatever is the value here and the value here, they are equal in magnitude, but opposite in sign. They just have one is negative of the other. The same way if I go another 180 degrees later, I will have the same thing. The value will be the same, just the sign goes on changing. So, this is what we have as half wave symmetry. You can go about constructing certain other examples also, which anyway we will revisit. See, and let me just give you one example of half wave symmetry. Let me say there is a waveform whose signal rises like this and then it is flat. Now, it falls down. Okay. Now, let us say from here it takes this shape. Now, this is t, this is t by 2. The signal rises from 0 to v in some some duration over some duration, and then it is flat at v till t by 2. Then it comes down to 0 and 0 it goes to minus v with some rate, which is same as here except for the sign. The slope here and here are equal, but just for the sign now. So, it goes down like this and it is here now. Is this waveform half wave symmetric? Is this half wave symmetric? Let us try and apply the condition now. So, let us say, let me just change the ink color for some clarity. Let me consider certain angle theta. Let me consider 180 plus theta. So, whatever is the value here, it is the same here, but for a opposite sign. Let me consider certain other instant. Let me consider this instant. If I go 180 degrees later, I have this. So, what you see the values here and there, they are the same except for the sign, that is this value and this value are the same except for the sign. So, this waveform also has half wave symmetry. There is something not so symmetric, it does not appeal to the eye. There is something not so symmetric. There are some additional symmetries which we will come to a little later, but this waveform nevertheless has half wave symmetric, because it satisfies the property that v of 180 plus theta is equal to minus v of theta. And this waveform you can be very sure that it has no even harmonic. You can try doing the multiplication, check it around yourself now. Maybe if you want, you can try that. You multiply this by a second harmonic sign. So, it would be like this. This is half cycle, this is one cycle of a second harmonic sign. So, this is like this now. So, if you take this green instant, whatever is the value here, the same value the second harmonic has here, but if you look at the original waveform, they are opposite in sign. So, if you add the product at this instant to the product at this instant, that is add the product at theta to the product at 180 plus theta, the sum is 0. This is valid for any theta. So, on the whole this reduces to 0. So, this is an example of a waveform which has half wave symmetry. It could be a little deceptive. You may at the first sight many students generally tend to say, well, it does not have a half wave symmetry, but it has, and that is the property, and that is how we define half wave symmetry here, and it has the meaning of having no even harmonic. Now, let us go further now. Now, within a half, is this waveform half wave symmetric? Yes, because you take this angle at theta and you take the corresponding angle at 180 plus theta, one is the reverse of the other. Now, what else does it have? It also has an interesting property that let me consider the middle here. Let me consider the middle of one half cycle of its fundamental of its let us say it is positive half cycle now. If I travel some distance from the middle and travel the same distance from this side, the waveform has the same value, is on top of quarter wave symmetry, half wave symmetry, it has this property. Remember, this waveform, the last waveform we drew here did not have this property, whereas if you look at here, you travel to the left or you travel to the right by the same distance, as long as you have traveled the same distance, it will have the same value. So, that is what we call as quarter wave symmetry. Let me call this as 90 degrees or pi by 2. So, whatever it is 90 plus theta is the same at 90 minus theta. So, whatever it is at 270 plus theta, the value is same as 270 minus theta. You also have the symmetry observed around 270 degrees. From 270 degrees, you go some distance to the right, or you go the same distance to the left, the waveform will have same values. So, you can look at certain other examples also before we go into that. Now, from the previous examples we had constructed a trapezoidal waveform. Some of this, this was one example we considered. This is a trapezoidal waveform, one time period t. So, this is t by 2. So, the waveform has half wave symmetry as we already seen, and now it also has quarter wave symmetry. It also has quarter wave symmetry. This is the middle point, this is t by 4. This is t by 4, and you go some distance to the right, go the equal distance to the left, the value is the same. So, let us say you go farther, the same, it is equal. So, it is symmetric about this t by 4 or 90 degrees. Similarly, it is also symmetric about, if you can just consider one half cycle and you take the central instant of the half cycle, what is that now? So, what is it that we are saying? We are saying that these are symmetric about 90 degrees and this is symmetric about 270 degree. What is special about 90 and what is special about 270 degrees? If you look at the waveform, let us say here, where is the fundamental component lying? Excuse me, where is the fundamental component lying? So, the fundamental component is something like this. The fundamental component is something like that. So, what we are saying as 90 degrees here and what we are saying as 270 degrees here are nothing but the instants at which the fundamental component is at its peak. The instant at which the fundamental component is at peak. Now, let us say theta p is the instant at which the fundamental component is at peak, any instant at which the fundamental component is at its peak now. So, if this property is satisfied in addition to half wave symmetry, we call this quarter wave symmetry. Let me just construct one other waveform here. Let us say a waveform like this. This is t, this is t by 2 and this is t by 4, and these values are, let us say if it is V 1, V 2, and these are the same values with the negative sign, minus V 1 and minus V 2. So, this has half wave symmetry and also has quarter wave symmetry. How do we say that? So, you consider this instant theta, you consider 180 degrees away or t by 2 away. So, what you have, it is the function has the same value, but for opposite sign, that is half wave symmetry. It has no even harmonic. On top of that, you look around this point, you go some distance and you go the same distance on this side, you find the values to be equal. So, this is quarter wave symmetry. So, someone can ask now, well, what is the significance of quarter wave symmetry? The significance of half wave symmetry is that there are no even harmonics. What is the significance of quarter wave symmetry? One answer to this question is, if you have half wave symmetry as in any of these cases, and if you want to find out the fundamental amplitude, what you normally do is you carry out an integration from 0 to 2 pi. Instead, you can only do an integration over 0 to pi and you can take this factor to be 2 upon pi. You can, let us say f of omega t, you multiply this by sin omega t, d omega t, and you do an integration to get the fundamental component. You do not have to do that, if a waveform has half wave symmetric, you do not have to consider the waveform over 0 to 2 pi. You can consider it from 0 to pi or from any theta to pi plus theta. You must consider one half cycle of the waveform. You can calculate your average over that. So, that is one of the advantages now. So, it reduces your calculation. If you have quarter wave symmetry, what you can further say is you need to consider only one quarter. For example, you can only consider this quarter, and you have this v of omega t defined only over this quarter, that is 0 to 90 degrees, and you perform an integration, that is v of omega t multiplied by sin of omega t. This is integrated with respect to d omega t starting from 0 to pi by 2, and then it is 2 upon pi by 2 or 4 by pi. This will give you the value now. So, this spares you the trouble of defining v of omega t from 0 to 90, that what you need to do. But if you want to do the calculation over entire cycle, you have to define v between 0 to 90, which is some equation. You have to define v between 90 to 180, it is another equation. This is another straight line. If you have to define v between 180 to 270, it is yet another equation. Between 270 and 360, it is yet another equation. If you have half wave symmetry, you do not have to define the waveform over the entire cycle. If you can just consider one half cycle and do that. If you have quarter wave, it is enough if you define the waveform just from the 0 to 90 degrees and you perform this integration over 0 to 90 degree, you can come up with your component. The same thing is possible for any nth harmonic component also. If for nth harmonic component, you are going to multiply this by certain sin n omega t and you are going to do this now. So, your calculation burden reduces. That is one of the advantages that you might have with quarter wave symmetry now. Then what could be the other one, like what are the significances what we have been talking about now. What you can say is, in a waveform that lacks quarter wave symmetry, or maybe we should first look at some examples where you have half wave symmetry, but no quarter wave symmetry. Of course, one of the examples I had already constructed. This is a waveform, which has half wave symmetry, but no quarter wave symmetry. Once again, to make my point clearer, I would say you consider this theta and you consider this pi plus theta. The values, you look at the values. So, one is the negative of the other. So, it has half wave symmetry. But if you look at quarter wave symmetry, you look at 90 degrees, you take t by 4. I do not know where it is 90 degrees, strictly speaking, but you see anywhere from here, the waveform is not really symmetric. The waveform is not symmetric about a particular line here. So, this lacks quarter wave symmetry. In such cases, what happens is, it is a little difficult for us to judge where the fundamental phase is. In a previous example, let us say if the same thing happens to be a trapezoidal wave, symmetric trapezoidal wave, we very easily say that the fundamental component is here. We say that this is the fundamental component. The phase of the fundamental component is clear to us, whereas the phase of the fundamental component is not very clear to us. And in cases where there is quarter wave symmetry, wherever the fundamental has 0 crossing, the harmonics will also have 0 crossings. The harmonics will also have, you may have another harmonic, the harmonic will have a 0 crossing here like this. Sorry, I am not, yeah. Whereas, where there is no quarter wave symmetry, wherever the fundamental has a 0 crossing, the harmonics need not have their 0 crossing. That is another issue. It gives you certain information about the phase of the harmonics. So, they are whenever the fundamental crosses 0, the harmonic also crosses 0, maybe from negative to positive or positive to negative, but they also cross. That is yet another thing that you have when you have when you do not have quarter wave symmetry. So, this is one example that I gave to show that waveform could have half wave symmetry and thereby have no even harmonics, but still not have quarter wave symmetry. I would give one other example. This is a waveform, this is time t. This waveform somehow looks nice, but has no half wave symmetry. If you consider this instant, if you consider a particular instant here and you consider the next instant here, this is not the negative of the other, this has no half wave symmetry. So, this is not basically an example of half wave symmetry, but no quarter wave symmetry, this has no half wave symmetry. This is an example of half wave symmetry, but no quarter wave symmetry. This is an example of both half wave symmetry and quarter wave symmetry. So, you can certainly construct various examples. Let me just take a triangular case. Let me say the waveform goes like this and then it comes back like this. This is time t and it continues. So, this is t by 2. So, if you take any instant like here, you consider some instant and a corresponding instant a half period away, the values are one is the negative of the other. So, it has even it has half wave symmetry and has no even harmonic, but this waveform once again lacks quarter wave symmetry. So, these are some examples that you can really think of, and as I mentioned earlier, this definition slightly vary. Some authors tend to use different definitions now. That is why I re-emphasize, for the purpose of this course, you will define quarter wave symmetry as here and half wave symmetry as here. That is V of 180 plus theta is minus V of theta. If the waveform satisfies that property, that is half wave symmetry, and if we have something like V of 90 plus theta is 90 minus theta, or more generally V of theta plus theta is equal to V of theta p minus theta, where theta p is the instant at which the fundamental component is at its peak, maybe the positive peak or maybe the negative peak. Theta p is the instant when the fundamental component is at its peak. This is theta p and this is also a candidate for theta p. Okay. Then we call this as quarter wave symmetry. If we have quarter wave symmetry over on top of half wave symmetry, then what we can say is the waveform not only has, you can say that it has no even harmonics, and you can say that you need to consider only 1/4 of the waveform starting from 1 0 crossing to the peak, for example, or any of the 4 quarters like this of the basically the fundamental cycle to do your PWM calculations. You do not have to define the entire waveform over the entire cycle. It is enough if you define it mathematically over 1/4. So, your calculation burden simplifies, and you can say something about the phase of all the harmonics. Whenever the fundamental crosses 0, the harmonics also cross 0. So, these are a few things that you can say when you have quarter wave symmetry too now. So, now this is all about a kind of a review of Fourier series, so that we can use Fourier series effectively to calculate the fundamental voltages and harmonic voltages of several different PWM waveforms. So, now the next issue is when the harmonic voltages are there, what are their effects is what we are trying to see now. Now, what gets applied to an induction motor, for example, like an induction motor fed from voltage source inverter is not only the sinusoidal fundamental component, also harmonics get fed there. Now, let us say we consider only the fundamental component. If you see only the fundamental component, it is a sinusoidal quantity. So, the fundamental component sees the induction motor as its fundamental equivalent circuit. So, which has the standard things. This is your rotor stator winding resistance, and this is the stator leakage inductance, and this is the magnetizing inductance, and you have a rotor leakage, and then this RR is once again the rotor resistance, and S is the slip now. So, this RR by S can be divided into two parts as RR and the remaining. The RR alone stands for the rotor resistance, and the remaining part stands for the mechanical power developed. The whatever power is dissipated through this resistor is equal to the mechanical power developed by the machine now. So, this is an equivalent circuit. What do we mean by that? So, when applied, when some fundamental voltage is applied, the current drawn by the machine is equal to whatever this fundamental circuit draws the same amount of current now. That is, there is a the terminal relationships are the same now. For a certain amount of fundamental voltage, whatever is the current drawn by the actual machine is the same as what is drawn by this circuit. So, this circuit gives us a measure of what is the stator current and what is the magnetizing current and what is the rotor current, and all these measures can be obtained from here now. And we can also see how much power gets dissipated here, and from there you can also come up with how much mechanical power is developed and etc. So, this is the fundamental equivalent circuit. The fundamental voltage, the inverter voltage has fundamental as well as harmonic components. The fundamental component sees the machine as some such equivalent circuit here, where the slip S is given by whatever is your synchronous speed omega S minus omega R divided by omega S. So, omega S is the synchronous frequency, that is, if you apply the stator frequency like 50 hertz or so, the revolving magnetic field revolves at its synchronous frequency, which is decided by the frequency of the applied voltage and the number of poles, that is something like that. So, this is the synchronous speed. The machine will also run at the synchronous speed if the machine is not loaded, but any machine has even under the so called no load condition has some amount of loading on that, and when you actually load it, what happens is there is a slip. The rotor speed is a little lower than the synchronous speed. So, that is what you get by the term omega S minus omega R, that is normalized with respect to omega S gives you the slip. So, the slip is 0 under no load condition, and the slip has some rated value of a few percentage, something like 5% or so, when it is under rated condition in many typical machines now. So, what happens is the slip is really low, and therefore, the term RR by S is significantly high. That is what we have, right. So, we move on. When we look at a harmonic voltage, let us say some instead of the fundamental component, some nth harmonic voltage, maybe the 5th harmonic or maybe the 7th harmonic is applied now. So, what happens now? In this case, as you find the slip, the synchronous speed is higher now. The fundamental is 50 hertz, the 5th harmonic is 250 hertz, the 7th harmonic is 350 hertz, and 5th harmonic also revolves in a direction opposite to that of the fundamental, and so the seventh harmonic revolves in the same direction. Now, the synchronous speed to start with is not omega s, but it is n times omega s, where n is the harmonic order. And the relative speed between the synchronous speed and the rotor is now, it could be n omega s plus omega r or minus omega r. It is n omega s plus r minus omega r. So, if it were the fifth harmonic, for example, this omega r and the synchronous the revolving magnetic field that the fifth harmonic produces are in the opposite directions. So, the relative speed is n omega s plus 5 omega s plus omega r. If it were the seventh harmonic, then the seventh harmonic's revolving magnetic field and the rotor revolve in the same direction, it will be 7 omega s minus omega r. So, this is what you have, n omega s plus r minus omega r, and you normalize it with respect to n omega s. If you do this, this is almost equal to 1, because n omega s is much higher than omega r. So, you have something which is almost close to 1 for high values of n. So, what you have is r r instead of r r by s. Now, r r by s is big because s is small, therefore, r r by s is big. So, if s is 0.05, r r by s is some 20 times r r, now it is only r r. R r by itself is only the winding resistance of the rotor, which is a very small number. So, what happens is it reduces, slip is close to 1, the rotor side resistance is now very low. Okay. So, you move to the next point. So, what you have is you basically had only the stator winding resistance and the rotor winding resistance, and when you are looking at harmonic frequencies, this omega L, this actually offers n times omega L, where omega could be the fundamental frequency. So, the harmonic frequency is n times omega L is the reactance seen by this, and n times omega L r is the reactance seen by that. So, this is the total reactance now. If you see these reactances, this n omega L s, for example, is much bigger than the rotor resistance R s, and similarly this n omega L r, the reactance pertaining to L r is much larger than R r at the harmonic frequencies. And therefore, you can ignore those two for the point of view of calculating how much harmonic current is being drawn, you can ignore those two now. If you go further, this inductance is much larger than this inductance. So, this inductance is practically like an open circuit, or the parallel combination of these two is almost dominated by this. It is almost close to this value of inductance, and that is what we get here. This is what is called as a harmonic equivalent circuit of an induction motor. A harmonic voltage that is applied essentially sees an induction motor as an equivalent as its total leakage inductance. So, if you want to calculate the IN, so this IN is simply equal to your Vn divided by n omega Ls plus Lr, is that right? So, this is the reactance pertaining to the leakage reactance. So, you can very easily calculate that. Now, you must remember that this equivalent circuit is mainly to calculate IN. You can calculate IN considering the resistances, for example, you can consider the various other things, but IN will not be significantly different even if you neglected those. But it, and you use this IN, it does not mean that there is no loss. This is to calculate, once you have calculated this IN, you can use this to calculate your copper loss. So, now the current harmonic, what we see is, if you take the stator winding resistance like what is indicated here, what flows through the actual stator winding is not only the fundamental current, also several harmonics flow. So, when IN flows, that it also produces IN squared RS will also produce the nth harmonic current also produces certain loss. So, the harmonic currents also produce the stator copper losses given by I squared R, and in fact, the resistance corresponding to harmonics could be a little higher because of high frequency effects such as the skin effect. So, the resistance could really be higher too, but we ignore those, and what we want to do is we want to consider the same resistance and want to be able to calculate a value of IN, and this is an approximation that is reasonably valid for calculating IN now. This is simplified analysis, you can add more and more details to it, but simplified analysis gives you a first cut figure which you can rely on, and also it gives you certain amount of insight. What is that insight? We will use this extensively. The harmonic, while the fundamental equivalent circuit sees the machine as some impedance, and that is a function of slip. The machine is seen as some impedance which is a function of slip, that is for the fundamental. But if you look at the harmonic equivalent, the harmonic voltage sees the machine simply as reactance. So, if you take a particular harmonic voltage and a particular harmonic current, they are related as though their relationship is similar to that of the voltage and current through an inductor. Now, this is of consequence, as we will see later. This will help us in analyzing the harmonic currents very effectively later on. Now, instead of a motor drive application, if you take it to be a grid connected converter, the line side is basically connected to the AC side of the inverter is basically connected to the mains through line inductor L. In that case, what you have is Vg is the mains voltage. This is what we saw in 1 or 2 lectures back. We were discussing front end converters and we were discussing StatCom kind of applications. This is the grid voltage, and this is the fundamental component of the inverter voltage, and this is the ripple part of the inverter voltage. The ripple has fundamental, the inverter output voltage, the terminal voltage has fundamental, which is at the line frequency, plus some ripple added to that. The ripple is the sum of all the harmonics. If you want the fundamental equivalent circuit, that is, you want to calculate the fundamental current drawn through this, then you can just ignore the ripple here. This is your equivalent circuit now. And if you are drawing certain amount of current I, you can even draw a phasor diagram. This is Vg and this is I that you want to draw, and the drop across the inductance due to I is going to be some j omega L. You subtract that, this is going to be minus j omega L I, and this is what is going to be your V inverter voltage. You can very easily draw even the phasor diagram and you can relate all the various quantities here. So, this is the fundamental equivalent circuit, and you move over, this is the harmonic equivalent circuit, which also we saw. So, here the fundamental components, the grid and the inverter do not make any effect here, and you can calculate your nth harmonic current simply using your nth harmonic voltage and the inductance here. So, these are the models which will help us calculate the harmonic currents in various applications, and based on those harmonic currents we may be able to calculate the copper losses, and we may be able to calculate many other things. So, what we have been looking at is this is a measure for calculating harmonic current, and from there we will be able to quantify some of the undesirable effects due to of harmonics, that is such as the increased copper loss, etc. now. So, as I mentioned, the purpose of pulse width modulation is to control the fundamental voltage and to mitigate the harmonics and their harmful side effects. So, we have reviewed Fourier series which tells us how to calculate the fundamental and the harmonic components, and we have developed models so that given a fundamental voltage or a fundamental current or harmonic voltage, we are able to calculate the corresponding fundamental current and harmonic currents. So, let us continue this in the next class and get into our business of understanding PWM effectively. I thank you very much for your interest and for your time and your patience, and I hope that you will have continued interest in this lecture series, and see you again in the next lecture. Thank you very much.